Hello, welcome to this latest edition of Silicon Grapevine. This episode is on AI-driven workflows, the future of design and IP management, and it's brought to you by the Electronic System Design Alliance, a semi-technical coalition. And my guest to talk about this topic is Dean Drako, who's a president, CEO, and founder of IC Manage and several other companies. But Dean, hello, how are you?
Good. Nice to be here.
Well, good. Well, I think we wouldn't sort of start without sort of getting a bit of your background. So tell us a little bit about your sort of journey in this whole EDA industry and in design industry.
Well, so a long time ago in the 1980s, I had my first job at Apple Computer, where I was a semiconductor designer, chip designer for the Mac, the new upcoming Mac. And
I have one sitting over here in my office.
yeah. And I was very frustrated with the tools. And so I took 2 weeks and just kind of was obsessed and wrote some new tools for debugging Verilog, which was a new kind of tool at that time. And our productivity went up like 100x with the new set of tools. And so I eventually, a year or two later, spun that out and created my first EDA company, which was called Design Acceleration. Eventually, I sold that to Cadence Design Systems, and to this day, it's the Verilog debug environment that Cadence sells. In 2003, after doing a few other projects, I founded Barracuda Networks, but I also founded IC Manage to do design management for chip design.
That's just over 23 years ago. Looking at your
23 years
profile.
ago, yeah. And we've been kind of leading the charge for design management for large-scale distributed companies with multiple design teams, and even the startups, soup to nuts, for those folks that really take their design management serious, want to do IP reuse, and in this new world, really want to apply AI agents to actually work on the designs along with the engineers so that they can get the maximum level of productivity, but also have confidence that the AI is actually using the right data and ability to check the results of the AI in a reasonable fashion.
Well, I mean, that sounds very simple, but it's not. Tell us a little bit about those trends that are making it not simple. I know we discussed with Paul Cunningham on a previous episode about all these agents and how they'll be so useful, but I think there's a little bit behind this still, which needs to be coordinated as well.
Yeah, I mean, I think AI is and will be and continue to be very powerful when it comes to chip design, semiconductor design. If you kind of think back a little bit, the origin of Synopsys was synthesis, which basically took kind of a language, Verilog or VHDL in those days.
Yes, I remember.
And converted it to gates. If you think about it, that is a really early form of AI. Okay, you're doing
that generation of the net list, for example.
Yeah, generate selection of the gates, optimization of the performance, minimization of the number of gates, and that synthesis tool was a very handcrafted AI. Okay, so it wasn't truly an AI; it was a rule-based system because it wasn't neural net AI. But the function of it, if you kind of take a step back, is the same function that we're getting from most of the AI today. Okay, and so that tool greatly increased productivity of the design engineers. Now with neural net AI, okay, we can actually provide a whole suite of tools, lots of agents, lots of tools, okay, that the engineers can use to do various types of design, optimization, fix bugs, do layout, do all kinds of things. I guess if you go back even further, the original place and route, okay, tools were basically a form of AI, although algorithmic, kind of a tool, a smart tool. Maybe AI is a little much, but a smart tool. And now I have agents, which, maybe will be even smarter. In all these cases, like you have to make sure that the data going into the tool is the right data, okay, is the right part of the design, the latest version or the correct versions. Then you've got to go basically make sure that when you get the results out, that you put them in the right place and that, that things are tracked. And so if you think about it, the design management problem, the problem that IC Manage tackles is coordinating 100 engineers or 1,000 engineers to make sure that they don't step on each other, accidentally overwrite each other's changes, okay, overwrite each other's files, that the latest things are available to all of them, okay, that the regression runs are running on the right things, etc. If you kind of say, oh, okay, we got 100 engineers, but now we got, 1,000 or 10,000 agents running, okay, that problem, basically grow, I don't know, 10x's, okay? And so you need to make sure that all of those agents are not stepping on each other, okay, are not overwriting each other, are getting the right data or the latest design or the proper design version, okay, to run their verifications, to run their designs, etc. And so all across the spectrum, I'm sure this was talked about before, those agents are going to be used for design, okay, solving problems, doing layouts, etc. Those agents are also, though, one of the most powerful places, I believe, will be in verification. And verification suite generation, okay, will be, able to generate more powerful, more comprehensive verification suites more quickly. But you have to run those suites on the designs. And so you got to distribute those designs to the compute farm. Okay. And those are all the problems that we solve at IC Manage with our global design platform.
Um, I mean, sometimes when we talk about all of this, the multiple agents here and the multiple teams, do you have examples of, like, maybe not naming customers, but examples where you've seen what people are doing and some of the challenges? I know you gave us some sort of indicative numbers, but some idea of a real design or something that you've seen through IC Manage or generally.
So I'm not sure I quite understand the question, but let me try and answer. Our customers are the largest of the largest customers in the semiconductor business. So every one of the large design houses, okay, and I won't name the names, but you kind of know who they are, the ones with trillion-dollar valuations, design every one of their chips, top to bottom, using IC Manage. Okay. And so, if you look at those designs that, used to be, a million transistors, then they were 100 million, and then they were a billion, and then they were, you know, it keeps going. Okay. Those chips are all designed using IC Manage and every file is coordinated by IC Manage and tracked. And in the end, the design is assembled, okay, by IC Manage and handed over to the fab to fabricate.
Okay. So then that's part of what I was asking. But then I guess also there's another element to this, which is the whole AI changing how the design cycle was and is. But on the one hand, we used to have like 2 to 3 design cycle, yes, like 2 to 3 year design cycles, and then AI was ultimately supposed to like compress that design cycle, and it is in some cases. But when you have
Yeah.
complex chips, what you're doing is doing a lot more complex stuff, but it's still taking 2 or 3 years, I guess. So yeah, it's kind of like helping in some ways, but also compressing some of the big complex chip design cycles.
Yeah, I don't think as an industry, okay, I think, the design teams are still getting their arms around how to leverage AI to reduce design cycles. Okay, I don't think the tools are starting, just started being delivered or were delivered last year. They're new tools, okay, being delivered by Synopsys, Cadence, Siemens, okay, and others, okay, that are going into the hands of the designers. The designers are then kind of going, okay, let's try this out in small scale. Let's have a few engineers try it. Okay, this seems to work. Let's start to roll it out. Let's start to use it. But they're also, you can't really afford to do a bad tape out. Okay, and so there's a lot of caution. The EDA and semiconductor design engineers are very, very modest adopters in the speed that they move of new technologies and new tools. And that's because, a tape out mess up is very, very expensive, and they want to be very, very sure. And so I don't think we've really seen the impact of AI on the reduction of design cycles. I think it's going to take a few years before that really impacts us as an industry.
Okay, I mean, there's another element to this, and which is basically what are the things maybe that are not well understood about how to use the agents and how to coordinate and orchestrate all of this. I think that might be a thing, obviously, which you help to do. But what fundamentally, what's the challenge still?
The challenge is, in some ways, no different than the challenge of coordinating large numbers of engineers. Okay. The agents are maybe puppets, controlled by the engineers. The objective is, if you think about it, right, maybe I have 100 engineers working on my design project, and it's going to take me, 18 months to get everything kind of wrapped and done. I either want to do that same project with, 20 engineers and take 18 months, or I want to do it with my, 100 engineers and do it in 6 months. Okay. Or, maybe I want somewhere in the middle where I'm doing 50 engineers and I want to do it in 12 months. Who knows? Right. There's different trade-offs that, the businesses will want to make. But the goal is going to be increased productivity of engineering, okay, in order to achieve a better business result. How do you do that? Well, you now are compressing or multiplying the amount of people or agents or entities working on the design. So if you kind of say, okay, in the old days, if I was going to compress that cycle from 18 months to 6 months, you can't really do this, but conceptually you could say, well, instead of 100 engineers, we'll put 400 engineers. 300 wouldn't do it. It's not linear. The goal would be to, kind of productivity. But now I have 400 engineers who are all trying to work on the same design. Okay. And so I have a partitioning problem, a stepping on each other problem, a big coordination problem, a how do I get, this done before that gets done? Do I have the latest version of that? Oh, somebody fixed that bug. Okay. Do I have that? All of this kind of stuff of trying to work through. And that's where design management, IC managed global design platform, GDP, really shines. Okay, that's the problem that we really address, is this coordination and execution. We accelerate the adoption of AI in many ways because that coordination is mostly handled. And if you kind of think about it, AI depends on data. What we provide with IC managed GDP is access to structured data, highly powerful, more powerful. Okay. And a lot of AI is designed to work on unstructured data. If you think about a chip design, it's the exact opposite. It's very structured data. It's well-known data. Okay. Now, one could argue that the Verilog code is pseudo-structured, but as you can see from Claude and Claude's ability to create code, right, it's actually quite structured. Okay. And the AI does really well in that zone because there's lots of examples and lots of information. Now, there's a little bit of a training problem with AI on Verilog and design data. All of it's super proprietary. Cadence, Synopsys, and Mentor have a huge problem getting data to train the models on. Okay, because they're big customers. None of their customers want to
Yeah,
share the data.
obviously.
Okay. And so there is this whole interesting thing in our industry of whether the companies will train their own AI models or whether will have, common models that'll be shared, developed by the vendors. And, both are happening. But in order to run AI, you need to have good quality data.
Part of that, I think you mentioned it right at the beginning in a different way, but I think when we had a conversation before, you talked about that one source of truth. If you've got hundreds and thousands of real engineers and AI engineers working on it, then I think there has to be a way of doing that, and I think that's what you were kind of alluding to as well.
Yes. We talk about with our customers the one source of truth, right? Because like one of the problems you have with 100 engineers is, where do I go? Does John have the latest or Bob have the latest? Where did he put the latest? And then I got engineers across the globe who are working in different time zones and different, schedules. They can't ask, where's the latest? Who's the latest? So you want this one source of truth, which you always know has not just the latest, but has, the various revisions, has clear tracking, has clear marking, has clear configurations. You need these 472 files, okay, pulled from these 18 different places in order to create this version, which allows you to run this test, okay, properly. It gets quite complicated because the chips are, crazy complicated.
Now, you said earlier, I mean, obviously, the big challenge is obviously because of commercial confidentiality, data sharing. So when they're trying to develop this one source of truth, is that obviously within their own clients, internal clients? I mean, how
Yes.
I guess you help them to do that, do you?
Yes. So the customers, the semiconductor companies, are also very shy about leaving data in the cloud, many of them. This infrastructure that we're typically talking about is internal network only. They may have servers in, 10 different countries, 5 different countries. Those servers are all being synchronized, okay, so that they all can be one source of truth, okay, and all have the latest and the relevant data, to the design team that's local there. So none of the design teams are waiting, hours for file transfers. And you get speed as well as, the ability for the AI to run off of the one source of truth anywhere in the globe at any time of day.
I do remember when I was working for a company in 1995 and the internet first started, and we had offices in Japan and the US and the UK, and how they were sharing, obviously rudimentary way, but sharing those data one source. But yeah, I guess it's a lot more complex now.
Yeah, well, in the early days, you would set up a script and you would say, okay, every night let's FTP the latest designs from Silicon Valley to the Japan office, and then they'll have it on their server. Okay. And then one night the FTP doesn't run because it gets an error or the network's down, and then they go and work on a design that's, a day old, and then you've got a mess and you got to go spend, 4 days sorting out the mess. Okay. Or we make a joke about, folks who basically, gzip and rsync or gzip and FTP and, all of these kind of crude mechanisms for trying to do this. That's the problem that we went and fixed at IC Manage with
Mm.
GDP. Now named, our new version is GDP AI, which incorporates a lot of capabilities to really meet the needs of these AI agents, as well as incorporates AI for queries into the design so that we can answer questions about the design for the customer.
What about the whole EDA lifecycle, the design and IP design lifecycle management? We haven't really talked about that.
That's a great topic. If you think about it, no chip today is designed from scratch. Okay. In the 1990s, okay, when you're doing a new design, okay, you would pretty much kind of start from scratch and you would redesign almost everything in it because you were in a new node, a new technology, leveraging, stuff from previous designs was not super critical because the designs weren't that large. Today, most of the design is leveraged from previous designs. Okay, and then you're also taking third-party IP, a Bluetooth interface or a Ethernet interface or a USB interface. Nobody's really going off and designing those from scratch because they want to get better performance out of them. Okay, there's no real great win for somebody to go redesign those yet again. You're trying to grab these modules either at a synthesis level, at a gate level, or sometimes at a layout level. At some level, you're leveraging these. One of the things is when you have these components or these modules, is you have to track them in your database, in your design management system, and be able to pull them in. But you got to pull in the right version, and you want to make sure that you're getting the version you want, because a module like this, a USB module, let's say a USB interface module, you will go through, you may find some bugs, you may have to tweak it for different technologies, you may have to adjust it, the interface on it to interface to a slightly different bus internally. So you might be modifying it, or you may be buying it from a third party and they may be providing you new versions, every 6 months or every 12 months or every month. You may have a specific one that you want to use because it's tried and true, or you have to make sure you get the one that has this bug fixed but not this. Okay, and so it's really important that you're getting the right versions of everything. And so you need to have a large, IP database where you're
Mm.
tracking all of this stuff. Has it been taped out before? Have we used this before? What nodes have we used it in? Has it been synthesized and laid out? Where are the different versions of the layout? We had to lay it out this way for that and lay it out this way for that. And so then when you're assembling your design, there's this thing of how do I find the right version and the right shape and size of what I'm looking for in order to bring it in? And then how do I continually make sure that I'm getting the right version when I'm doing my assembly for both my verification, my layout, and then eventually for tape out? And so the IP management task and IP tracking, okay, is a huge part of everything we do in GDP AI in order to provide tools for these, engineers to assemble these behemoth chips.
I've seen in the past from the EDA companies these silicon lifecycle management solutions. So you complement that, or I mean, how does that, or are they doing that specifically for their own IP?
They're typically doing that for their own IP or for a single module. They don't really tackle which we tackle is, hey, what is all of my IP in my library and which which ones have been taped out where and what's been used and who worked on it, what is it capable of and what are the parameters. And so we have a database that's, massively extensible where each of our customers basically establishes the structure and the methodology that they want to track their IP, what parameters are important to them, and then have the ability to organize it, search it, find it. And then, most importantly, once they've found it, actually pull it into the design and assemble it, right? Because if you think about a design today at the top level and then the level below and the level below, it's really an assembly kind of issue, right? Because I'm pulling hundreds, thousands, millions of components together, and I got to make sure I get the right ones. And so, how do I track that and do that is, a key component on top of the life cycle management of the components.
You have lots of experience, and yeah, I mean, what excites you about what's going on with AI in EDA right now? I mean, you live and breathe it every day, as do the whole industry now. But what's the most exciting thing that you think is on the horizon, or that you excites you?
There's a number of things that excite me. Okay, one is AI is a dislocation event.
Mm.
Okay. And so if you think back in the history of kind of the computer industry, we've had a lot of, what I refer to as dislocating events. So invention of the PC was a dislocating event to the mainframe industry. The concept of client server and then over the network was a dislocating event. The network was dislocating. The internet was a dislocating. Mobile kind of smartphones was a dislocating event. Okay, social media was a dislocating event. But when you have a dislocating event like this, which AI is definitely one of those, there's a massive number of opportunities created for entrepreneurs. Applying AI in these industries gives an opening for new companies and new entrepreneurs to step in. So I find that fun and exciting. On the other side, we have basically semiconductor business has all of a sudden become important to the world again. Okay. Whereas we were kind of, the EDA business and the semiconductor business were kind of like, not particularly interesting to anyone. And all of a sudden, overnight, okay, we are in the limelight as an industry. Okay. Whereas, the last 20 years, we've kind of just been quiet and in the background. And most of the people in the world, had forgotten about us or didn't know about us. And so that's kind of fun and exciting. And then we've got a whole new opportunity in front of us for AI chips to basically, I mean, the chips that are doing the AI stuff today are relatively powerful and amazing, but they weren't really designed for it from the ground up. Okay, and so there's this huge opportunity for us as a society, an industry, as a team to basically go and really do great chips for this and kind of 10x it from where we are today because we'll reduce the power consumption, we'll reduce the data center electricity consumption, we'll reduce, all of these environmental issues that everyone's worried about. There's this big opportunity in front of us to basically go use great engineering and solve that problem.
I'm going to ask you a little bit of a controversial end to that, which is, do you foresee a disruption? You talk about dislocation event, disruption in the EDA business models and the big EDA companies having to figure out what's next. But also, I think 2 or 3 years ago, I wrote about EDA 2.0, a new emerging EDA startups that are doing some of these things using EDA tools that the big companies have done in the past? I mean, it's kind of controversial. You don't have to answer, but you might have some thoughts.
I think there'll be some opportunities for some new EDA companies to, innovate and create some things. Okay. But I don't think the business model is fundamentally going to, shift, and we're going to end up with, Cadence and Synopsys going out of business, or anything kind of drastic. The amount of technology in the stack, the amount of understanding, the amount of tooling that they provide to the customers is really insurmountable, for a new company to come along and do at this point. Okay. And if you think, one of the major companies could go and kind of replace all of those tools with internal versions that, they used AI to build, I think that is not viable with the complexity and depth of the technology stack. It's really about depth of the technology stack in my mind, right? Because you start with, maybe I want to do a chip, but I got packaging issues. I got everything from, high level Verilog to place and route to design validation and verification of the layout, analog synthesis. Okay. And it just like the depth of the stack and technology is really, really hard
Yeah.
to overcome.
Well, it's interesting because historically we've seen, like your company, many other companies, when these startups come up, then Synopsys or Cadence or Siemens see a value in adding that to their stack. And I think that's kind of how it's played out. But I was just a little bit playful in thinking, will things change? But I guess
What might be interesting is we might see some, higher end, bigger companies who have the budget actually invest in maybe doing a better version of one level of the stack. They're unhappy with the place and route or the module routing or the DRAM routing, some routing tool or some piece or tool that they get from vendors, and they may go build their own kind of middle piece in order to get a technology advantage or a market advantage. I can see that happening. Just replacing the whole stack at this point, really hard. When I was doing chip design myself, even in the early 90s, we developed a bunch of tools internally, synthesis tools and all kinds of things. But things have progressed so far since then that I think it's very difficult.
All right, final question. And I guess, what are the fundamental things you've learned through your career that will be a guide to maybe younger people wanted to consider coming into the EDA industry? Because if they keep hearing about all these agents taking over, they may not come in. What's your big lesson in life that you'd like to offer to people to say, well, look, this is a great industry, or this is what I really learned about it all?
Yeah, I would say one of the things that I often talk to younger folks about, especially ones who want to be entrepreneurial, is what I call these dislocations or events, right? And those are opportunities, not something to be feared, but something to be taken advantage of, right? And we're in the middle of one right now, so there's lots of opportunities flying about. So I would kind of say that that's a lesson that I've seen over the last 40 years. Yeah, long time. The other lesson is when building or tackling or building a career, expertise in a zone that goes very deep, okay, is always valuable. Whether that expertise is in writing C code, which not a lot of people do these days, but an expertise in a knowledge space is not in the tool space. So like being an expert in C isn't going to be super valuable these days. Maybe it is, but like not as valuable as it used to be. But if I'm an expert in algorithms for layout, okay, now that's got value because that's how to solve the problem, not knowledge and expertise in the tools to solve the problem, if that makes sense,
It
right?
certainly
I'm an
does.
expert analog circuit guy. There's value in that. Now I can use Claude and maybe do that, but in the end, there's not a whole lot of circuits to well, I guess there is a lot of stuff in academia and stuff that's been documented to train the AI on in analog circuits. If you have an expertise in a zone, that becomes very valuable rather than just an expertise in the tools.
Dean Drako, thank you very much for coming on as a guest on Silicon Grapevine. We'll talk to you again in future shows.
All right. Well, thank you very much for having me and having such a good discussion about IC Manage and our GDP AI design management tool. It's been a great fun. Thank you.
Thank you, Dean.